Welcome to this scientific lecture on the microcapsule buckling onset paradox. Today we will explore a fascinating phenomenon where capsules can buckle like elastic shells, yet the onset of buckling contradicts classical elastic criteria, suggesting hidden viscoelastic or phase change physics in the shell material. Let's begin by understanding what we mean by a microcapsule. A microcapsule is a spherical shell structure, typically ranging from 1 micrometer to 1 millimeter in diameter, consisting of a thin membrane encapsulating a liquid or gas core. Here we see a cross-section of a microcapsule. The shell thickness is h, typically tens to hundreds of nanometers. The radius r is much larger than h, giving us a slenderness ratio h/r that is very small, typically 0.01 to 0.1. Classical elastic shell theory, developed by Timoshenko and others in the early 20th century, predicts when a spherical shell under uniform external pressure will buckle. The critical buckling pressure is given by this equation: 2e divided by the square root of 3 times 1 minus nu squared, multiplied by h/r squared. Here e is the Young's modulus, nu is Poisson's ratio, h is shell thickness, and r is radius. Let's do a back-of-the-envelope calculation. Suppose we have a polymer shell with Young's modulus E equal to 1 gigapascal, Poisson's ratio nu equal to 0.3, thickness h equal to 100 nanometers, and radius r equal to 10 micrometers. E equals 1 gigapascal, nu equals 0.3, h equals 100 nanometers, r equals 10 micrometers. The ratio h/r equals 100 times 10 to the minus 9 divided by 10 times 10 to the minus 6, which equals 0.01. The critical pressure is approximately 2 times 10 to the 9 divided by 1.7 times 0.01 squared, which gives approximately 1.2 megapascals. This prediction seems straightforward. We expect the capsule to buckle at approximately 1.2 megapascals. But experiments tell a completely different story. Now let me describe the paradox that has puzzled researchers for years. When we compress microcapsules between parallel plates or subject them to osmotic pressure, we observe buckling. But the pressure at which buckling occurs does not match the classical prediction. Here's a schematic of the compression experiment. 2 parallel plates apply force to a microcapsule. As we increase the force, we measure the deformation and look for the onset of buckling. Let me pose a question. What do we observe experimentally when we compress these microcapsules? The answer is striking. Buckling can occur at pressures significantly lower or higher than the classical prediction, sometimes by factors of 2 to 5. This is the paradox. This graph illustrates the paradox. The green line shows the classical elastic prediction for buckling pressure. The red dots show experimental measurements from different capsules. Notice the scatter. Some buckle much earlier, some much later than predicted. So why does this paradox occur? The answer lies in the fact that the shell material is not purely elastic. There are hidden physics at play. The first hypothesis is viscoelasticity. Real polymer shells exhibit both elastic and viscous behavior. The material response depends on the loading rate. A simple model of viscoelasticity combines a spring representing elasticity with a dashpot representing viscosity. The spring element stores energy, while the dashpot dissipates energy through viscous flow. In a viscoelastic material, the effective modulus depends on time or loading rate. If you load quickly, the material appears stiffer. If you load slowly, it appears softer. The time-dependent modulus can be written as E of t equals E infinity plus E0 minus E infinity times E to the minus t over tau. Here tau is the characteristic relaxation time. Now here's a critical question. How does viscoelasticity affect the buckling pressure? The answer is that fast loading gives a higher effective modulus, leading to higher buckling pressure. Slow loading allows stress relaxation, giving lower buckling pressure. This explains part of the scatter in experiments. We can write this as critical pressure for fast loading is greater than the elastic prediction, which is greater than the critical pressure for slow loading. The second hypothesis involves pre-stress and residual stress in the shell. Manufacturing processes often introduce internal stresses that are not accounted for in classical theory. During fabrication, the shell may develop compressive or tensile pre-stress. Compressive pre-stress, shown here by inward arrows, can significantly lower the buckling threshold. When pre-stress sigma 0 is present, the effective critical pressure is modified. The buckling can occur at lower external pressures if the shell is already partially stressed. We can write the effective critical pressure as the classical critical pressure minus alpha times sigma 0, where alpha is a geometric factor and sigma 0 is the pre-stress magnitude. The third hypothesis concerns thickness variations. Real microcapsules do not have perfectly uniform shell thickness. Local thin spots act as stress concentrators. This diagram shows a capsule with a thickness defect. The thin spot on the right side has locally higher stress concentration. Buckling will initiate at such defects at lower pressures than the uniform shell prediction. The stress at a thin spot can be several times higher than the average stress. If the local thickness is h' equals 0.8 h, the local stress can be 25% higher. The local stress is approximately the average stress times h over h'. This amplification can trigger early buckling. The fourth and perhaps most subtle hypothesis involves phase transitions in the shell material. Some polymers can undergo glass transitions, crystallization, or liquid crystalline phase changes under stress. Here we see a schematic phase transition. On the left, the polymer is in an amorphous state with random molecular arrangement. Under stress, it can transition to a more ordered crystalline state on the right. This transition changes the mechanical properties. A phase transition can dramatically alter the elastic modulus. A polymer transitioning from amorphous to crystalline can increase its modulus by a factor of 2 to 10. The crystalline modulus is approximately 2 to 10 times the amorphous modulus. This sudden stiffening can delay buckling to much higher pressures. Let's now examine the buckling process itself in detail. What actually happens at the microscopic level as we approach and pass the buckling threshold? Stage 1 is pre-buckling. The capsule undergoes uniform compression. The shell remains spherical, and the deformation is purely membrane stretching with no bending. Stage 2 is buckling initiation. Small perturbations grow unstably. Here we see a mode n equals 3 perturbation developing. The shell is no longer perfectly spherical. Stage 3 is post-buckling. The deformation grows into large amplitude mode. Here mode n equals 4. The shell exhibits significant folding and bending. Energy is now stored in bending deformation, not just stretching. Here's an important question. What determines the buckling mode number n? Why do we see mode 3, or 4, or 5? The answer is that the mode number that appears is the one that minimizes the total elastic energy at the buckling transition. Classical theory predicts this. The optimal mode number is approximately the fourth root of 12 times 1 minus nu squared times r squared divided by h squared. For our example with r equals 10 micrometers and h equals 100 nanometers, let's calculate the expected mode number. N is approximately the fourth root of 12 times 0.91 times 10 to the minus 5 squared divided by 10 to the minus 7 squared, which gives approximately 5.7. So we expect mode number around 5 or 6. Now let's think about buckling from an energy landscape perspective. This gives us deep insight into why the paradox occurs. We start with the equilibrium equation for a thin spherical shell under uniform pressure. This is a differential equation for the radial displacement. Del to the fourth w plus pr squared over d times del squared w equals 0. Here w is the radial displacement, d is the bending stiffness, and the operator del squared is the Laplacian on the sphere. The bending stiffness d equals eh cubed divided by 12 times 1 minus nu squared. This explains the strong dependence on thickness. D equals eh cubed over 12 times 1 minus nu squared. Notice the h cubed dependence. We seek solutions in the form of spherical harmonics. The displacement can be expanded as a sum over mode number n. W of theta phi equals the sum from n equals 0 to infinity of an times ynm of theta phi, where ynm are spherical harmonic functions. Each mode number n has an associated critical pressure. The lowest critical pressure determines the buckling threshold. Pn equals d over r squared times n plus 1 times n plus 1 minus 2. This gives the critical pressure for mode n. Minimizing this expression over n gives the optimal mode number and the classical critical pressure we saw earlier. Let me now summarize the key physical insights we've gained from this lecture. First, microcapsule buckling is not purely elastic. Time-dependent viscoelastic effects are crucial and cannot be ignored. Second, the loading rate strongly affects the buckling pressure. Fast loading gives higher thresholds than slow loading. Third, pre-stress and thickness variations cause significant scatter in experimental measurements. No two capsules are identical. Fourth, thermal fluctuations become important at the nanoscale and can trigger premature buckling. Fifth, stress-induced phase transitions can dramatically alter material properties during loading, creating unexpected behavior. Based on this understanding, I can offer practical design guidelines for creating robust microcapsules. Guideline 1. Always characterize the viscoelastic properties of your shell material at the loading rates relevant to your application. Guideline 2. Control shell thickness uniformity during synthesis. Even small variations significantly affect buckling. Guideline 3. Account for processing-induced pre-stress. Annealing or controlled drying can minimize residual stress. Guideline 4. Design for time-dependent stability, not just instantaneous loading. Your capsule must survive over its entire lifetime. Guideline 5. Test capsules under realistic conditions including temperature, humidity, and chemical environment. Laboratory tests may not reflect real use. This buckling paradox connects to many other fields. Let me briefly mention some fascinating connections. In soft matter physics, similar buckling phenomena occur in vesicles, liposomes, and polymer shells. The physics we've discussed applies broadly. In mechanical metamaterials, controlled buckling is used to achieve exotic mechanical properties. Understanding buckling allows us to design materials that buckle on demand. In biology, cell membranes and whole cells exhibit buckling. Red blood cell deformation in sickle cell disease involves buckling mechanics. In aerospace engineering, thin shell structures in spacecraft and aircraft face similar buckling challenges. The lessons from microcapsules scale up. We have explored the fascinating paradox of microcapsule buckling. While capsules behave like elastic shells, the onset of buckling often contradicts classical elastic theory. The resolution lies in hidden physics. Viscoelastic effects, pre-stress, thickness variations, and possible phase transitions all contribute to deviations from classical predictions. A complete understanding requires the combination of careful experiments, rigorous theory, and detailed numerical simulations. This knowledge enables the rational design of functional microcapsules for applications ranging from drug delivery to food science to materials engineering. Thank you for your attention. I hope this lecture has given you a deep appreciation for the subtle physics underlying microcapsule buckling and the beautiful interplay between elasticity, viscoelasticity, and structural instability.